Okay, so this is the 2023 Higher Level Leaving Cert Maths paper 1, question 3. And in part A here we have to prove that square root of 2 is not a rational number, that square root of 2 is an irrational number. So this is one of the standard proofs that you have to know for the Leaving Cert, and it is going to be a proof by contradiction. So what we're going to do first here is assume that the square root of 2 is rational. That means that it can be written in the form, square root of 2 can be written in the form a over b, where a and b are integers and b is not equal to 0. Also, we have to say here that the highest common factor of a and b is 1. In other words, a over b here, the fraction a over b is written in its simplest form. So we could have a fraction 2 over 4, but it's not in its simplest form. So in its simplest form, the highest common factor of the a and b here would be 2, so it's not 1. So we would just write it in its simplest form here, 1 over 2. The highest common factor of 1 and 2 is 1. Okay, so this is where we start anyway. Next thing we're going to do is just square both sides. So this gives us 2 is equal to a squared over b squared, and that gives us 2b squared is equal to a squared. So let's just mark that one there. What we're saying here is that a squared is twice b squared. Now remember, a and b are both integers. So if a is an integer, a squared is an integer. If b is an integer, b squared is an integer. So a squared is twice some integer. That means a squared must be even. A squared is twice some number, so therefore a squared must be even. So we would say something like as b squared is an integer, a squared has to be even, which means that 2 divides a squared. If 2 divides a squared, then 2 divides a. Now that means a is equal to twice some other integer, we'll call it k. So k is an integer as well. So if 2 divides into a, then a is twice some integer, and we're calling that k. Now remember, what we've shown so far is that our fraction here is a over b, and we've shown that a, the top number here, our numerator, is divisible by 2. The second part of this proof here is what we're going to do is we're going to prove that b is also divisible by 2, which contradicts this statement that we made up here that the highest common factor is in fact 1. So that contradicts our whole assumption that root 2 is rational. So let's just continue on down along here then. So we have a is equal to 2k and k is some integer. So what we can do now is just square both sides here. So we have a squared is equal to 4k squared. Now remember here that a squared is in fact 2b squared up here, so I'm just going to change that. A squared is 2b squared, so that's equal to 4k squared. I'm just going to come over here now, I'm running out of room. So divide across by 2, that gives you b squared is equal to twice k squared. So again here we can say that if b squared, which is an integer, is twice some other integer squared, then b squared is divisible by 2. This means that b squared is divisible by 2, which means that b is divisible by 2 also. If b squared is divisible by 2, then b is divisible by 2. Okay, so at this stage what we've done is we've shown here that 2 divides a and 2 divides b. That contradicts our statement up here that the highest common factor of our original fraction a over b is 1. The highest common factor is in fact 2. So we just need to make a statement here then. Okay, so what I'm going to say here then is 2 divides a and b. This contradicts the assumption that the highest common factor of a and b is equal to 1. Therefore, root 2 is irrational. Okay, so that's it for part A. Let's have a look at part B. Let's see, t is a positive real number with log t to the base 3, log t to the base 9, log t to the base 27, log t to the base 81 is equal to 10. Find the value of t. Give your answer in the form 3 to the power of r, where r is a rational number. And it's giving us a hint here. This is the changing base rule in your log tables. So we can use that to change the different bases here. So I'm looking at the numbers here. Our bases are 3, 9, 27, and 81. They're all multiples of 3, which is handy. So what I'm going to do is change log to the base 9 to the base 3, log to the base 27 to the base 3, and this one here as well, log to the base 81 to the base 3. So let's do that. So we have log t to the base 3. Let's see, then we also have log t to the base 9, so I'm going to do log t to the base 3 over log 9 to the base 3. That's using this rule here. Plus log t to the base 3 over log 27 to the base 3 plus log t to the base 3 again over log 81 to the base 3. All of that is equal to 10. So if I write that out again, I get log t to the base 3 plus log t to the base 3 over log 9 to the base 3 is just 2. 3 to the power of 2 will give me 9. Here we have log t to the base 3 over log 27 to the base 3. Well, 3 to the power of 3 will give me 27, so 3 is what we can write there. And here we've got log t to the base 3 over log 81 to the base 3. Well, 3 to the power of 4 will give me 81, so this is just 4, and that's equal to 10. Okay, so what I'll do is, again, I might just move this down a little bit, just to give myself some room here. Okay, so next line then, I've got a 2, a 3, and a 4 here. So what I'm going to do is multiply everything by 12. So let me see here. This is going to be 12 log t to the base 3 plus 2 into 12 is 6 log t to the base 3. 3 into 12, that's 4 log t to the base 3. And then 4 into 12 is 3 log t to the base 3, and that gives me 10. So let's see, I've got to multiply this by 12 as well, so that's actually 120 here. So it's kind of a common mistake to forget to multiply this by 12 as well. Okay, so let's see, what have we got? We've got 12 plus 6, that's 18, 19, 20, 21, 22, 23, 24, 25. So we end up with 25 of these log t's to the base 3, and that gives me 120. That gives me log t to the base 3 is equal to 120 over 25. I can divide top and the bottom by 5. So that gives me, let me see, 24 over 5. So finally then I will get, if I convert from log form into index form, 3 to the power of 24 over 5 should be my answer. Now let me just see, what way did they want this answer? Give your answer in the form 3 to the power of or, where or is a rational number. So 3 to the power of or, and that is a rational number, 24 over 5. So that's it. That's as far as I can go with that. Let's move on to the next question then. It says, explain what log m to the base 6 means where m is a positive real number. Log m to the base 6. So log m to the base 6 is a power. Let's see, where the power is what you need to raise 6 to get m. Something along those lines. You may have written this differently, but this is by no means a formal definition. This is just first thing that comes into my head here. So it's log m to the base 6 is a power, and that power is what you would raise 6 to get m. So again, it's you may have written this slightly differently, but that's a general kind of a definition there. So let's see what part 2 asks us to do. We've got m is a real number and m is bigger than 6. What information does this give you about the value of log m to the base 6? So if m is bigger than 6, that means log m to the base 6 is greater than 1. Why? Because remember, this is a power. This is what we need to raise 6 to get m. And if m is bigger than 6, remember 6 to the power of 1 will give me 6. So if log m to the base 6 was 1, so if log m to the base 6 is equal to 1, that would mean that m is equal to 6. But m is bigger than 6, therefore log m to the base 6 has to be bigger than 1. So again, you may have written this differently, but this is my kind of explanation for it. Log m to the base 6 is greater than 1. What information does this give you about the value of log m to the base 6? It just means that log m to the base 6 must be bigger than 1. Okay, so that's it for this question.